Thanks, Elizabeth, for the introduction. And so I will talk about non-resonantly driven nutation by ultrashort laser pulses. And first of all, before starting, I would like to thank the organizers of this workshop for giving me opportunity to talk here. So let's first talk about ultrafast magnetization dynamics. So what happens when an ultrafast or ultrashort laser pulse hits a ferromagnet? So when an ultrashort laser pulse hits a ferromagnet, then first of all, the electrons are excited above the Fermi level. And when the electrons are excited, then the excitation is transferred to the spins. So spin system is also excited. So we have a system of hot electrons and spins. And so due to this thermalization of electrons and spins, the magnetic material basically loses its phase memory and it gets demagnetized. So this thing happens within first few hundreds of femtoseconds. We call it region 1. I will come to it later. So after that, it tries to relax. It tries to regain its original condition. So the excited electronic and spin system, they dissipate heat to the lattice first. We get region 2 in first few picoseconds, and then afterwards the system dissipates the excitation or heat to the surroundings, and we get region 3, which occurs about like hundreds of picoseconds. Okay, so we have measured this ultrafast magnetization dynamics by time-resolved magneto-optical Kerr effect by it is an all-optical technique. So we have used an optical probe, an optical pump, and optical probe to excite and detect the dynamics. So this is the setup you can see. So now let's come to the sample system, which I will discuss in this talk particularly. So we have done the measurements in a thin permalloy film. It is like 80% nickel and 20% of iron, so Ni80 Fe20. And the thickness we have taken for this particular study is very thin. It is 5 nanometer and 2.8 nanometer. They are like deposited on MgO substrate with an aluminum oxide capping layer. So the samples are fabricated by molecular beam epitaxy. Basically, Laura fabricated the samples. And we have done the measurements in polar Moog geometry with a slightly tilted applied magnetic field. And we have used like 800 nanometer laser 2 pump and 400 nanometer to probe the system. So as I talked about the 3 different regions of magnetization dynamics, so here is a typical one experimental result. So this is the result from the 5 nanometer permalloy sample at a particular pump fluence and applied magnetic field. So here in this region 1, as I discussed, it is the ultrafast demagnetization, which occurs within first few hundreds of femtoseconds. Then there is the region 2, that is the fast remagnetization due to the dissipation of heat to the lattice. And then we have the second or slow remagnetization superimposed with a precession, which occurs within like hundreds of picoseconds. Okay. So I will discuss about these 3 different regimes separately. So first, let me focus on this first region, that is the ultrafast demagnetization region, which is supposed to be an extremely or highly non-equilibrium state. So generally, in this type of thin films with in-plane magnetization, generally people follow the longitudinal Moog geometry to study the ultrafast demagnetization. But whenever we want to study the precessional dynamics, so we have to do the measurements in a polar geometry with a slight tilting of the magnetic field. So first we wanted to see, is there any difference between this ultrafast demagnetization in this both geometry? So eventually we have found that the ultrafast demagnetization in these 2 different, it do not basically depends on the geometry of the Moog. So we have fitted the demagnetization traces in these 2 different geometries in polar and longitudinal Moog by this phenomenological 3 temperature model to extract the demagnetization time and the fast remagnetization time. So we have found that when we have increased the pump fluence or excitation fluence, the demagnetization time, remagnetization time, as well as the amount of quenching, they increase steadily with the increase of pump fluence. So we can say that as we have deposited the sample on a insulating substrate, So no spin transport is possible, and also the extracted values of Dmag times are basically slow. If spin transport is considered, then the demagnetization would have been more faster. But here the extracted values of demagnetization, so and their behavior, it confirms that there is a spin flip scattering dominated ultrafast demagnetization in our systems. So after this, we want to focus on the region 3, that is the precessional regime. Okay. So we know that this third precessional dynamics is basically governed by this Landau-Lipschitz-Gilbert equation, where this first term on the right hand side is the precession term around the applied magnetic field, and the second term is basically was later added by Gilbert with the Gilbert damping term. So this effective H effective is the effective magnetic field acting on the spins, which not only consists of like external magnetic field, but with the anisotropy field, dipolar field, exchange field, and the contribution of all give this effective field. So first we have done this precessional measurements at different magnetic field strengths. So here you can see the two different data set at two different magnetic field strengths. So when we fast Fourier transform this time resolved data, then we get the spin wave or Magnon frequencies, and when we have plotted the frequencies versus magnetic field and we have fitted the data with the Kittel formula, then we can extract the saturation magnetization of the sample, which is like similar to what we obtain in permalloy. But then the interesting thing is, like we have fitted this time resolved data with the damped sinusoidal function to extract or calculate the lifetime of precession. So what we have seen, like these red dots, it is basically the extracted lifetime of precession or Magnon lifetime from TR-MOC measurements, and this black line is obtained from analytical calculations, and these blue lines are measured by like microwave spectroscopy measurement, normal VNA FMR technique. So we have seen like completely opposite behavior or trends of this lifetime with applied magnetic field. So then we were wondering that why this is happening. So what may be the plausible reason for this behavior? So we have come to the conclusion that when we hit the sample with a femtosecond laser pulse, or we strongly excite the system with the laser pulse, then in addition to coherent magnons, some thermally generated incoherent magnons are also present, which is like responsible for this opposite behavior, because this is not the case in case of like the normal microwave spectroscopy measurements, where no thermally generated incoherent magnons are present. And when we apply the magnetic field strength, so as we have applied a tilted magnetic field, so when we increase the magnetic field strength, then the out of plane component basically increases, due to which the percentage of incoherent magnons reduces when we increase the magnetic field. So to again confirm this observation, we have done some fluence dependent measurements. So we have increased the pump fluence and then measured the time resolved dynamics, and then again have done the same treatment, that is fitting the data with the sinusoidal function to extract the lifetime. So here again we can see that when we increase the fluence, the lifetime basically decreases, because when we increase the fluence, percentage of incoherent magnons or thermal magnons basically increases as compared to coherent magnons, due to which the lifetime decreases. So from this precessional dynamics, we confirm or can conclude that in this dynamics, in addition to this coherent precision, some incoherent magnons are present. So after that, we are basically interested to see the what happens between this region 1 and region 3, because you know that region 1 is the highly non-equilibrium region created by the laser pulse, and this region 3, it is like close to equilibrium region. So how the transition occurs from this highly non-equilibrium region to this close to equilibrium region. So for this thing, what we have done, we have taken the data, time resolved data, up to first few hundreds of picosecond with a much higher temporal resolution. So then we can see some high frequency oscillations superimposed on top of this precession. Like this inset is a zoomed view of one portion of this data set. So there you can see that on top of this precessional background, there are some high frequency oscillations present. So then we have subtracted this precession or ferromagnetic resonance background, and then we have done the fast Fourier transform of this background subtracted data. So then we can see that there is one peak around 0.1 terahertz. So then we have done the same measurement for the 2.8 nanometer permalloy sample. It's a more thinner sample, and again we have seen some high frequency oscillations present on top of the precessional background, and after reduction the ferromagnetic resonance background, again we can see there is a high frequency oscillation at 0.1 terahertz. So after this, to really confirm that this mode is appearing or not, we have taken data for these two different sample thicknesses at different magnetic fields and different pump fluences. And then we have taken a small portion of the time resolved data set and then have like swept through the data set and have performed the fast Fourier transform in each consecutive data. So then we can see, we can get like a frequency versus time plot for these two different samples at like different magnetic fields and pump fluences. And in every case, in every frequency versus time plots, we can see that there is a mode around 0.1 terahertz present in every cases. So the frequency, this frequency basically remains almost invariant in like with the variation of the sample thickness or the variation of pump fluence or magnetic field. And these high frequency oscillations are non-resonantly excited in our case with the application of just optical pump and optical probe. So then we are trying to understand that what may be the origin of these high frequency oscillations. So what happens when we hit the sample with the femtosecond laser pulse? So as we have told that we have taken a in-plane magnetized permalloy sample here. So the anisotropic field is in the plane, but we have applied a tilted magnetic field, so the effective field lies somewhere in between. So now when we hit the sample with the femtosecond laser pulse, then it is well known that the anisotropic field basically changes, due to which this effective magnetic field becomes time dependent for a very short time. And then what happens, the angular momentum, it takes a new orientation, and then the angular momentum precedes around the new orientation of the effective field. But when we hit the sample with the femtosecond laser pulse, so then the effective magnetic field becomes time dependent for a very short time scale. And when the effective magnetic field becomes time dependent within very short time, then basically the magnetization or the magnetic moments cannot instantaneously follow the angular momentum. So angular momentum precedes around the new orientation of the magnetic field, but for the initial time scale, the magnetic moments on the magnetization cannot instantaneously follow the change. So it first precedes, or we call it nutates, around the angular momentum, and then on longer time scale both becomes parallel and both precede around the effective magnetic field. But on very short time scales, their dynamics are basically separated. So if we consider this thing happens due to inertia, and if we consider that this inertial term is also present in the Landau-Lipschitz-Gilbert equation, so then we are left with this inertial Landau-Lipschitz-Gilbert equation, where this third term is basically the inertial term, giving rise to these high frequency oscillations on top of precession, which are basically known as nutation. So this nutation has been theoretically predicted like few years back, but experimentally till now only one group has reported its existence, but they have done the experiments with the resonant excitation of nutation by terahertz pump optical probe. But in this case, we are getting this high frequency nutation oscillations even if we excite the sample with the non-resonant optical pump. So after that, some atomistic spin dynamic simulations have been done to confirm that the frequency is due to the inertial term in the Landau-Lipschitz-Gilbert equation, and these simulations are performed by this group of Professor Ulrich Nowak in the University of Constance. And when they have simulated the system in presence of this inertial term in the Landau-Lipschitz-Gilbert equation, then they have also seen some high frequency oscillations on top of precession, and the frequency also matches with the experimentally observed values. So in this figure, you can see that how the magnetization initially nutates around the angular momentum, and on longer time scale, both of them become parallel and precess around the external magnetic field. So to summarize, so using an all optical femtosecond laser pulse in time resolved mode, we can excite the nutation superimposed on the precessional dynamics, and this high frequency nutation oscillation, they cannot be explained by these conventional Landau-Lipschitz-Gilbert equation, but we have to consider the additional inertial term in the Landau-Lipschitz-Gilbert equation. And this nutation frequencies are almost invariant of like excitation fluence or the applied magnetic field. So with that, I would like to acknowledge my postdoc supervisors like Martin, Georg, and Philip, and also my collaborators Benjamin and Ulrich, and my co-workers Akira, Laura for sample fabrication, and Julius for giving me support with the simulations. And I would also like to thank all other group members from my university, SPIN+X, for giving me the fellowship for my postdoctoral research. And thank you all for the attention.